Carol, thank you all for having me. It's a pleasure to be back. So I thought I would give a little kind of survey of Bob's contributions to the n-valued fixed point theory, which is it's nice to see some people going to be talking about this over the week, along with, and this will include a very basic introduction to the general setup of the Nielsen fixed point theory, in case anyone is a little bit unfamiliar. Here's a picture. I have some pictures also of Bob. I thought I'd start off with some personal remarks about Bob. This is from Bob's website, which is still available if anybody would like to see it. This is Bob, I think, at UCLA.
Yeah.
This is what I would describe as his favorite outfit. I noticed in looking at all the pictures. He is always wearing sort of a blue shirt with a collar. When it's cold, he wears this sweater over it, but usually not. I'm not suggesting that he only owned one shirt, but I think he probably had several of the same kind. Here's another picture. I decided to type in. This is, I don't know if you recognize this little thing. This is generated by an AI image creating service called DALL-E. And you can type in some words, and it will make you a picture of what you wrote. So I typed in illustrative cartoon image for a talk about Bob Brown's n-valued fixed point theory and some of my own. And this is what it said, which is pretty good, I guess. This maybe looks a little bit like Bob, although the shirt is the wrong color. Maybe this is me, or this, I don't know what that is here. And it does say Bob, so that's pretty good, I guess. As Peter mentioned, Bob had 20 PhD students, and here's a little timeline of where they were. And this red one, that's where I was, towards the end there. It seems to me that Bob's students kind of came in waves. There was the early batch here, some in the middle, and then some later on. Although this, I'm tempted to say this is near the end, but it's not really. I mean, he was still teaching for 10 years after the last batch there. There are some things that I can think about why is it like this? Why not so steady? One suggestion is that this reflects the times of intensive interest in Nielsen theory. Maybe I don't think actually that's true. That there were waves of popular interest in Nielsen theory.
A different version of one of those.
Oh yeah, okay. I think there could be sort of economic factors at play, but I would suggest that a major factor in this is that, and this is really what I want to say about Bob, he was kind as a person. And I think that he tended to have a lot of students at once, because he would have a student, and that student would tell their friends, I really like Bob. He's a good person to work with. He's kind. I understood when I was a student at UCLA, just talking to other students who were further along in the program, I always understood that Bob was a nice person to work with, which I think, those of you who are, we can all remember being students, that's actually a very important thing. It's not just, are they doing the kind of mathematics that I want to do? That's certainly important. But is this really a person that I want to meet with every week and have them ask me questions about what I've been doing and try to explain to them? I think that's very, very important. And I think Bob's kindness is a big part of why we're here. I would say that this group of people, this research community, is distinctively made up of kind people who interact with one another in kind and generous ways. This has always been my experience. I hope that's been your experience too. And I would say that this is a reflection of the way that Bob wanted to create a community. And he was very successful at creating a community of kind people. And this is really, Bob's legacy. As we see the talks this week, I don't know about this time around, but usually, not every talk in Nielsen theory mentions Bob Brown. But I think there is a taste of his spirit in the way that we interact with one another, and I'm very thankful for that. I have some pictures of Bob also. This is us at the Poland conference in 2009. Here's me and Ning there. That's Bob in the middle. And then Chrissy Soderlund and Aaron Wright, who are two of the other people in our group Peter mentioned. This is us in China, me and Ning and Bob. Bob was yelling, I think he's saying, Joel, because Joel, this here's Joel came over and joined in the picture. Joel Better was another student of Bob's. This was us. The rest of the pictures I have are all eating. So this was a dinner at a conference in Korea. That's Sungwon Kim. You can see Peter in the back there, and I believe this is Daseberg and Sasha. Yeah. And there's Vácek right there. And this is Evelyn Hart. And this, I think, maybe Yuzurski. Any guesses? I don't know. Here's a different dinner in Korea. That's Phil Heath in the middle, and this is Sungwon's wife and Bob there. This also, I believe, is from Korea. Here's Carol up here. Is it the same shirt? Maybe. No. I'm focused on the shirts. Here is Ning and Timur, and this is.
I have that picture.
Yeah. I hope I'm not using Ning's picture. She has some pictures also. This is a Bob. Notice this is a yellow shirt, so he does maybe towards the end of his career, he got some more variety in this shirt. But he still has the pens in the pocket. Yeah. Yes, yeah. As he was more comfortable in his position, maybe. I was recently at a workshop at the American Institute of Mathematics, which is near Berkeley. And they have a giant collection of old prints of research articles that were donated to them by fairly famous mathematicians who, at the end of someone's career, you have a bunch of stuff. And for me, probably they'll just throw everything away. But for some people, they collect them. And I was happy to see Bob had a little binder here with some of his papers in it. This is from the, I don't know if you can see down here, this is from the collection of Victor Klee, and this is the paper on the fixed point theorem for compact maps, which Peter mentioned. So I was pleased to see him being collected in that way. What I would like to talk to you about this morning is his work in the n-valued fixed point theory. So from 2006 to 2023, there's a brand new paper. Bob wrote 12 papers as far as I can tell, in the n-valued fixed point theory. This constitutes most of his output during those years. Bob actually wrote another sort of a survey paper for more or less a general audience, but I like the title. His title was "A Good Question Won't Go Away." And I think this is true of Bob and sort of the things that he chose to work on. It was always my impression that Bob worked on the things that were interesting to him. He was not trying to chase the Fields Medal, or he was not after the hot topics. He was just doing things that he liked. Others became interested too. This is how these things became interesting to other people. So I want to talk about the n-valued fixed point theory that Bob worked on, and a little bit about a new paper of mine in related things. I hope you won't mind if we just look at each of these 12 papers for a couple minutes. The n-valued theory, I would say in general, it seems simple at first, and usually everything kind of works out the same way as the ordinary single-valued fixed point theory, but it's not always the case. Sometimes things are more interesting than you expect them to be. Anyway, this is the setup. We're going to talk about an n-valued map. So an n-valued map from x to y is a continuous multi-valued function where f of x is a set of exactly n distinct points. It has to be exactly n different points. So exactly 2 points all the time, or 3 points all the time. Never less and never more. And a fixed point means it is a point. So for this, you consider n-value maps from the space to itself. And a fixed point means x is an element of f of x. So that's the setup. So the picture that you should have in mind, or what I have in mind when I think about this. Single-valued fixed-point theory, you usually think about pictures like this. So when I draw a picture like this is the graph of a function from the circle to itself. You know, as Peter mentioned, we pretty much always talk about compact domains. So this is the circle, so consider this as like the interval, but with the endpoints identified, which is why this curve can go off this side. It has to come back at the same point over here in order for it to be continuous. And also, because the codomain is the same, the graph can also go off the bottom and come back off the top. So this is continuous. And I have also highlighted this diagonal line as the line f of x equals x, and the fixed points are the intersections of my original graph with that diagonal line. I hope everybody's familiar with this idea. So this is the picture from single-valued maps. For n-valued maps, it's more like this. This is a picture of a 3-valued function. That means for every x value here, if you look vertically, there should be exactly 3 y values. I hope that I drew this properly. But anyway, you can do more or less the same thing, right? This time I would, again, look at, if you think about points where x is an element of f of x, it still looks like the same situation. You're looking at intersections with the diagonal line. So most of the tricks that you play for the ordinary single-valued theory, it works the same way for this. All right? A little sort of prehistory to Bob's work. Bob did not invent the n-valued fixed-point theory, although he's probably written more papers than anybody else on the subject. There were 3 papers by Helge Schirmer that Peter mentioned. In 1984, another one in 1984, and then 85, Helge did a simplicial approximation for n-valued maps, and then an index and a Nielsen number for n-valued maps, and then a Veckan theorem for n-valued maps. And then at that point, apparently, Schirmer just kind of packed up her suitcases and left the area. That was it for n-valued fixed-point theory. Nobody did anything with these papers until Bob sort of, I would say, revived the theory in 2006. So there was a long time of, little to no interest, and then Bob became interested in 2006, and then there were still several years of little to no interest, but eventually the rest of us became interested also. So the first one of these papers was in 2006, and the paper, Bob's first paper in the area, has no references later than Schirmer's paper in 1985. If you look at his references, he is just picking up as if the day after her paper, but it was 20 years after. So here's a very quick review of the basic definitions by Schirmer. Like I said before, this is more or less like the single-valued theory. And one thing that works very, very nicely is the fixed point index. So if you only consider near one of these fixed points, the fixed point index is a local invariant, so you can look just nearby, and then it just looks the same as a single-valued fixed point index. So we use the ordinary fixed point index, and there is essentially no funny business with the index for the n-valued theory. The fixed point classes are slightly more complicated, but not so bad. So for the single valued theory, it's like on the signs or whatever, this on your name tag. You see that. Thank you to whoever made this. I don't know who. I just copied it. So this is the fixed point classes for single valued theory, and you do basically the same thing, although it's a little more complicated. So for the n-valued theory, I am drawing this as if it was a 5-valued function. So here I have x and f of x. X is one of those points in the set f of x, which is 5 points total. And then you also have y is another fixed point. F of y is all of those other points. And these 2 points are in the same class if there is a path like this from x to y, such that when you plug it into the function, you get the picture on the name tag. Although it's a little more complicated because when you plug this into the function, you get 5 other paths, which are the f of alpha, but it gives you 5 things every time. And they have to be different, so actually, like, these paths are not allowed to cross each other, but they don't, so it's okay. But anyway, the relation is the same thing. So it just says that when there is some alpha, so that one of those 5 paths has this homotopy property, that alpha is homotopic to f of alpha. So it's pretty much the same. All right. Schirmer made these basic definitions and then proved some theorems about it. But Schirmer did not do many examples. This is something that Bob used to tell me about the difference between Helga Schirmer and Bob Brown. He said Helga was not interested in doing examples. I think Peter mentioned that. And Bob was very interested in doing examples where you can actually compute the Nielsen number. So anyway, Bob's first paper works out the theory entirely for maps on the circle, n-valued maps on the circle. He shows that, well, every map on the circle has a linear version. You know, those pictures that I was drawing with the curved graphs, you can just sort of pull everything straight and you make it into what he called the linear map on the circle. And a linear map, actually, these are all the same as what he called power maps. That is, like, if you think of this as the circle as complex numbers of length 1, they are all, you know, like the square root is a 2-valued map, and so on. Other roots give you other n-valued maps. And Bob showed that every circle map is homotopic to one of these linear maps. And then once you have the linear maps, it's fairly easy to compute everything that you want to know. And in particular, you get this formula for the Nielsen number, which is very nice. If you remember, this formula for the single-valued fixed-point theory is a 1 minus d. In the n-valued theory, you get an n minus d. That's nice. All right. That was the first one. Number 2, I'm going to try to get through these in my time. I think it'll be fine. If I go late, that's just lunch, right? But I actually have a deep respect for lunch. So, number 2 is the Lefschetz number for an n-valued multi-map. This was the next year. So Schirmer gave a definition for the index, but she did not discuss the Lefschetz number. But actually, the index is, I don't know, in my opinion, the index is like a more complicated version of the Lefschetz number. So that you should be able to do the Lefschetz number easily if you already know how to do the index. So it's obvious to define the Lefschetz number like this, as the sum of the fixed point index, because that's how I think of the Lefschetz number usually. But this, I would say, this is against Bob's old school upbringing. The Lefschetz number, in a traditional sense, is something you compute using the homology, a trace of the homology, something like that. So this should not be the definition of the Lefschetz number. It should be defined as a trace sum in homology, and then we prove this is a theorem, not a definition. So the point of this paper was to give a definition using some kind of something about the trace of something, and then prove that that formula is true. So anyway, how do you define the Lefschetz number? You want something like this, the induced map on the homology, but the f is n-valued. So this thing kind of is n-valued, but you don't want it to be n-valued because you want to take the trace of it. So you have to do a little bit of thinking about this. As usual, it's good enough to do this on the chains because of the theorem that says that sum of the traces on the chains is the same as the sum of the traces in the homology. So we don't really have to think about the homology. Let's just look at the chains. If you have a simplex u, then f of u is going to be a union of n different simplices. That is, I'm going to assume that I chop up the triangulate sufficiently finely so that each individual simplex goes to n disjoint other simplices. So for a simplex, f of u is a union of n different simplices. So we just sum up those simplices. So each column, we make a matrix like we usually would here. Usually this matrix, each column of the matrix tells you where does this simplex go. And it has one non-zero entry in each column, typically. But this time, each column is just the sum of the n appropriate simplices. So this matrix that we make here would be one in which typically a column would have n different non-zero entries. Everything works out nicely. And then Bob proves this theorem. If you actually use those matrices, like I said, and add them up in this way, you get the sum of the indices, which is what he called the Lefschetz number. And you get, of course, the Lefschetz fixed point theorem because of this. And then Bob also proves on the circle, this is not so hard if you just linearize everything, that the Nielsen number is the absolute value of the Lefschetz number. And then this is the formula for the Lefschetz number. So, great. All right, that was number 2. Are you still with it? Number 3 is Nielsen numbers of n-valued fiber maps. As Peter mentioned, fiber maps was a major theme for Bob. And unfortunately, Peter stole my joke here, but Bob also said this to me. This is the best way to get 2 papers accepted to the annals, is if you sort of fool them into accepting the first one, which has errors in it, and then you have to publish the correction. Yeah, that was something he said to me. Something that I noticed, I don't know if there's any if there's any meaning to this. In his first, in these early papers about fiber maps in the Annals, he spelled fiber, F-I-B-R-E. But then in this one, the multi-valued, it's ER. So, a little something to notice. Anyway, Bob is trying to enlarge the type of n-valued maps for which we can compute the Nielsen number, right? Before this paper, it was basically the circle. That was it. And so it's a slow journey to consider more and more types of spaces, but this is a big step, I suppose. He gives the familiar formula. This is basically the formula that comes up when you read his old papers, and he does the same thing in this paper for n-valued maps. Really, I would say this paper is kind of no surprises. It's just what you think works, and it works. The fourth one is called Coincidences of Projections and Linear n-valued Maps of Tori. This was actually 3 of these papers that I'm going to discuss were written with undergraduate research students. They would do these summer projects with undergraduates, and this is the first one of that type. And in this paper, they define what it means to be a linear n-valued map on a torus. So this is similar to those linear circle maps, but on a torus. Something interesting, though, on a circle, everything you can straighten out and become linear. But on a torus, it seems that there are some examples of maps which are not homotopic to these linear ones. So this does not describe all possible maps on the tori. But anyway, they proved this nice formula in terms of this determinant. This should look familiar if you've seen that the determinant formula for the Nielsen number on a torus. It has the usual formula is just determinant of the identity minus a, but this one has some extra n's in there. All right. This formula actually, I'm not sure if this is always true, but in this paper at least they prove it with some hypotheses on the entries of the matrix. All right. That was number 4. Number 5 is called Nielsen Coincidence, Fixed Point, and Root Theories of N-Valued Maps, and this is also with an undergrad student, Kolahi. This does some simple coincidence theory for n-valued maps, and this is something like this is an example of 2 n-valued maps, and I'm going to try to do coincidence theory of these 2 things. These are 2 different 2-valued maps, and I want to know, well, coincidence theory, in general, Bob defines what I will call a geometric coincidence theory. The geometric, I'll say what I mean by that in a moment, but it's looking at just all of these points when the 2 things cross one another. This is the definition of the coincidence set that Bob used in this setting. It's all the points in the domain X where there is some point in common between f of x and g of x, which are 2 sets of 5 points each or something. He calls this m comma n valued coincidence theory because it's actually, in this case, these are 2 different 2-valued maps, but it's actually not important that they both have the same number of points. So you could have a 2-valued and a 3-valued. It doesn't really matter. So he called this m comma n valued. The f and the g can have different values of points. One thing I will just reiterate, this is counting the number of x's which are intersections of those 2 things. So you're counting the number of points in the domain, all right? This theory is very weird. I had never really appreciated this. I didn't really read this paper very closely until last week when I was sort of getting ready for this talk. But it's very strange. For example, coincidence classes can behave in strange ways. Well, I didn't tell you what a coincidence class is, but it's what you think it is, or it's what you imagine it is, even if you hadn't really thought about it. They can behave in strange ways. For example, here is a very simple example. These are linear circle maps. Each one is 2-valued. And in this arrangement, they have 4 coincidence points. All right? I'm going to change the blue one a little bit. Watch this. You have to watch carefully. I'll go back and forth a little bit. The blue one is changing. All right? What is different? Now there's only 2 coincidence points. They have joined up or somehow doubled up together. But this is not the same as when 2 fixed points join and the index doubles up, right? It's not like that. Because actually, well, it's just not. And in fact, whatever you think the coincidence classes means, these are not in the same, this x1, x2 are not in the same coincidence class. You can look at the path, that means you take a path from x1 to x2. and plug it into the function, do you get a path from this one to this one? You don't in this example. These are not in the same coincidence class, but in fact, this is like an epsilon homotopy. You can do this by arbitrarily small homotopies. Those will combine into the same coincidence point. Very strange. This is now, it's as if you have two different coincidence classes are able to combine. Yeah, this is what I said. Using a homotopy, you can sort of combine coincidence points, which would seem to be in different coincidence classes. Very strange. And this maybe is all I'm going to say about this. This is interesting, and I don't fully understand this still. I was going to say, this is why I said Bob defines a geometric coincidence theory. He defines a class as being essential means that it can never be removed by a homotopy, which in making that definition, rather than using the index, you can somehow get around some of these theoretical questions. But I think this is interesting to me still. Anyway, the next one, construction of multiply fixed n-valued map. So what he means by multiply fixed just means it has multiple fixed points, more than one fixed point. And in the homotopy class, the minimum number of fixed points is always more than one. And Bob's idea for this paper was, can we create lots of examples? That's what the title says, construction of multiply fixed n-valued maps. And he has a little sort of a simple trick for this. If you start with a single valued map, you can choose an n-fold cover, and then you can use that cover to, you do this little thing here, and what you get is an n-valued map that's sort of based on your single valued map that you started with, together with the structure of the covering that you use. And then Bob gives a formula for this n-valued map. That's a formula for this, which is in terms of the Nielsen number of the original function. It also involves the stabilizer subgroup, so this is not a trivial formula. But anyway, this provides many examples where the Nielsen number is strictly greater than 1. That's this paper. Yeah, not just on circles and tori. This is what Bob was interested in, is doing examples on more general spaces than that. All right, the next paper, stabilizers of fixed point classes and Nielsen numbers of n-valued map. This is basically a continuation of the previous one. This is with another undergraduate student, Nan. Continues the previous paper. He gives, for example, a class of maps on graphs, which were not considered in other papers, where that same trick that you do, you start with any map that you want on the graph over here, and then the Nielsen number of this thing with the cover is n times the original Nielsen number of the graph. So you can get arbitrarily high values for this by using those coverings. All right. Number 8 was called On the Topology of N-Valued Maps. This is with Dacieberg Gonçalves. Maybe I'll point out here, I hope Dacieberg won't mind me saying this. I talked to Bob around when they started working on this project, and Bob was very pleased to be working on a paper with Dacieberg. He was, you had not worked together before this, is that right? Yeah, so Bob and Dacieberg had known each other for a long time, but never actually wrote a paper together. And I think in some ways Bob saw this as the moment when the n-valued maps started to get some respect. The fact I was talking to him about it, and the fact that, oh yes, Dacieberg is now interested. That was the sign that things have really gotten serious. So I thought I would just quote, this is the first sentence of the abstract. This paper presents an exposition of the topological foundations of the theory of n-valued maps. That's exactly what this paper is about. It's actually not about fixed point theory. The term fixed point does appear in the paper, but it's only in the references, and they sometimes say something like, this might be of interest to people studying the fixed point theory, but really this is not a paper about fixed point theory. It's about the definition of an n-valued map, and some other things too, but this is what I will sort of highlight. A lot of what they say in the paper is already known results, but it's sort of nicely packaged in a way which is easily readable to people like us. So this is about kind of foundational definitions about n-valued maps. So an n-valued function, I never really told you what this meant at the very beginning. I just said it's continuous. But what do I mean by continuous? So the definition typically used, say by Shermer, is that it is both lower and upper semi-continuous. I'm also not going to tell you what that means, but that's a standard definition. You don't have to know what that means. Lower semi-continuous and also upper semi-continuous. If it's that, then we say it's continuous. And here's the big theorem from this paper. The following are all equivalent under light assumptions on X. Light assumptions, I mean things like Hausdorff and second countable, so they're not even compact, very light assumptions. First of all, F is an n-valued map. This is equivalent to upper semi-continuous. So actually in this definition, you don't need lower. If it's upper, then automatically it is also lower, and so therefore continuous. Also, something they call sequentially continuous. This is a standard definition of continuity in terms of limit points of sequences. This is also equivalent. Also, this is an interesting one. X to dn of y is continuous. This dn is the unordered configuration space of n points. So that is the set of all sets of sort of tuples of n points, but not, I shouldn't say tuples because you don't care about their ordering, all right? So, and this has a standard topology that is typically used on the configuration space. And so this, being an n-valued map in the sense of Shermer, is actually the same as being a continuous map into the unordered configuration space. It means that a lot of these things, you could say in a very simplistic way, you could say fixed point theory of n-valued maps is really just the same as fixed point theory of these maps. Single valued map from X to dn of X. Although that doesn't really make sense what I said. You can't talk about fixed point of this map because it's not from one space to itself, but okay. And this is also equivalent to F being Hausdorff continuous if Y is a metric space. Hausdorff, there's something called the Hausdorff metric of subsets of a metric space. And if you can think of a multi-valued function as being continuous with respect to that metric, that's the same as everything else. All right? This is a nice little result. This is not the kind of thing that you need to prove all of your theorems, but I think it's a nice way of tying up kind of the foundations of the theory. Number 9, the two-sphere is Veckan for n-valued maps. This is with Crabb, Eriksson, and Stimpson. So Eriksson and Stimpson are other undergraduate co-authors. Crabb is not, I've actually never met Michael Crabb, but he is he's older than me, I guess. He's not an undergraduate. Working in the UK somewhere? Anybody know?
He was in Aberdeen.
Aberdeen, okay,
And
yeah.
he retired and he is in the rest of England.
Okay, retired now. Congratulations. Crabb, throughout the last 10 years or so, has been working on kind of another n-valued theory, which is in many ways very similar, but using different foundational definitions for everything. And so a lot of what we have been doing in the kind of Nielsen theory of n-valued maps is actually similar, or in some cases exactly the same as other things that Crabb has done. So he's an important person to follow. Anyway, the first sentence of this paper says, we prove the theorem of the title. That's really all you need to know. The two-sphere is Veckan. Veckan means that the Nielsen number is equal to the minimum number of fixed points of a self-map. Yeah, this could be the entire abstract. I think the abstract is longer than that, but that's it. This is interesting to me because all n-valued maps of the sphere to itself split into two different single-valued maps. This is because the sphere is simply connected, and that implies that any two-valued map, I said two, I should say all n-valued maps split as n single-valued maps, all right? And from that point of view, I feel like, okay, then if you understand n single-valued maps individually, that should tell you everything you need to know about the n-valued maps. But it's not so simple. So this is just about, the two-sphere. This is non-trivial, even for a simply connected domain, which in Nielsen theory, usually if it's simply connected, everything is much simpler. There's only one fixed point class, but this is not a trivial proof that they use here. All right. And the problem arises because, Veckan means you can always change the map by homotopy to have the number of fixed points equal to the Nielsen number. If you just start with two single-valued maps, by the classical Veckan theorem, you can change each of them by a homotopy to realize their individual Nielsen numbers. But while you are changing the two maps together, their values may at some point collide so that you don't actually have two distinct values. And this is the problem. You have to show that it's possible to change two maps at the same time while keeping them separate from one another. And that's not trivial. All right, number 11. That was number 9. I'm skipping number 10 temporarily. Number 11 is on the Nielsen root theory of n-valued maps from 2021. And Bob does sort of basic constructions for root theory for n-valued maps. Root theory is like this. You take a map. It no longer has to be a self-map now, but you just choose a specific point in the codomain, and then you look at what are all of the points which map into that point. So in single-valued root theory, this would say A equals f of x. But in the n-valued theory, we use this. A is an element of f of x. All right, so the Nielsen root theory of f and some point A is like the coincidence theory of f with a constant map. But it's not exactly the same, or at least not obviously, because the homotopies that you use are homotopies only of the f. You don't, in coincidence theory, typically you change both of the maps by homotopy. In this case, you only change the f. You don't also change this A as if it were a constant map. You don't also change that by homotopy. All right, so a picture would be, here's a single, just a map by itself. And if I choose A to be, 0, or the base point, then these are the roots. All right, so Bob proves a root finite simplicial approximation theorem, and he defines a root Nielsen number in this setting, and then gives you formulas for linear circle maps and torus maps for the Nielsen root number. All right. And then number 13, lift factors for the Nielsen root theory of n-valued maps. And this was his second paper with Dassenberg, which just came out, May, right? Very, very recent. So recent that I haven't read the whole thing. I hope you'll forgive me. But this is a continuation of Bob's paper that I just mentioned. This defines a lifting classes point of view for the root theory of n-valued maps. And it's similar, but algebraically simpler than the lifting classes for n-valued fixed point theory. And this is the paper that I skipped over. There was number 10, which I said I was going to talk about later. The time is now to discuss lifting classes for the fixed point theory. So this was number 10. This is the last one of Bob's papers that I'm going to talk about. Lifting classes for the fixed point theory of n-valued maps. This was 2020. This was written with Charlotte de Koninck and Carol de Kimp and me. I was glad to, I talked to Bob about this. It took us a while to finish the paper, but it was several years before, and I was glad to. I brought this to Bob. I said, "Hey, why don't we try and do this, lifting classes?" And he said, "I've written a lot of papers with my students, but it was always my idea first." So I'm very pleased about that. Anyway. In Helga Schirmer's original work, the fixed point classes were not defined using liftings, which is actually, I believe, the historical way that the fixed point classes were originally defined in the very old days. But Helga used this path thing. Schirmer used this, the thing on the name tag, to define the fixed point classes. Like this picture that I showed you from before. Schirmer did not attempt to define lifting classes for the fixed point theory. Maybe because it's more complicated. This is, not so complicated. It should be possible to do this with liftings as well. And this is what this paper in 2020 was about. I'll give you the basics. For single-valued maps, so this is just, in the single-valued case, this is how we typically do it. You start with your ordinary function, and then you look at liftings to the universal cover space, and you consider various covering motions applied to a specific, you just choose one lifting, and then you look at all the different covering motions applied to that lifting for a particular alpha in the fundamental group, the deck transformation group. And you say that x and y are fixed points in the same fixed point class if this basically says they are fixed points of the same lifting, not exactly the same. It could be alpha f and beta f, where alpha and beta are related according to they are the same, we call it the same Rademeister class, which is this relation, this twisted conjugacy relation. So this is the 30-second version of the single-valued lifting classes theory. Let's try to do this for the n-valued in the n-valued setting. So in this case, instead of x to x, of course, we have, I'm going to write it this way. This is the way that this whole paper is written with this kind of configuration space point of view. So we have a map from x into the, remember, this is the unordered set of configurations. How do we consider the lifts of this map? This is the initial question that will have you thinking for a little bit. How do we consider lifts of this? Do we do this? This is, you lift x to the universal cover of x and then consider unordered configurations on that. Or maybe this, the universal cover of the configuration space. Or maybe you ask yourself, aren't those the same thing? And then you think for a few minutes and you say, no, they're not the same thing. This is kind of bigger than that. So which one should we use? Or maybe neither of those? The answer is neither of those. Neither of these is what we want. We want a cover which is kind of universal enough, but not too universal for this setting. This thing is not big enough. This is not big enough to be the universal cover because, you know, the universal cover is supposed to be like the top. You can't cover any more than that. But this unordered configuration space cover is covered itself by the ordered configurations. Every ordered configuration, you can just forget about the ordering, and that's a cover from the ordered to the unordered. So if you go this far, that's definitely not the universal cover. It can go even further. So you might want to go this far. But actually, this is too big because this one would allow configurations like that. This is a configuration of 2 points, x and some covering motion of x. Those are 2 points. But in terms of what we want to consider about the projecting this thing down to the base space, these do not represent 2 different values from x, which we don't want to consider configurations like that. So the proper, at least as far as we determined in this paper, the proper covering space to use is something called the orbit configuration space. And this is ordered configurations of endpoints, which avoids this kind of situation. So these are ordered configurations where no one of these is a covering transformation of one of the other ones. Another way to say that is they never project down to the same point at the bottom. So this is what the lifting classes theory is based on, lifting to this cover. It's not the universal cover, but it's pretty universal, all right, for our purposes. So this is a covering map. If you think about it, the covering group of that thing is this semi-direct product. If you just think about, if I'm starting up here, what are the ways I could make a covering transformation of these things? They look like n separate points. They look like this, right? Well, one way you could do that is like in the first coordinate, I could do any of the ordinary covering transformations, or in the second coordinate. So that's where this pi 1 to the n comes. You can do ordinary covering transformations in any of the coordinates. And then also, you could permute these elements, and this is another covering motion. And if you put those together, they interact in this semi-direct product. All right? And so any map here, and here's the details of the lifting classes, any map here lifts automatically to a map here. And these will automatically split. That's because the domain is simply connected, and there's an old theorem that says if the domain is simply connected, then the map splits as n different single-valued maps. All right? And then F induces a homomorphism like this, which is slightly weirder than the classical situation. That homomorphism you can write sort of in factors. There's n parts here, and then 1 part here. So that's what that is. And then each fixed point comes from a lifted point like this. And then we say x has Reidemeister class alpha comma I. So this means that when you go up to this lifting, x comes from a fixed point of fi, not a fixed point, but one which permutes down to this other covering motion of x. All right. So each fixed point has a Reidemeister class of that form. And then the twisted conjugacy type relation that we use is this right here, which is a little more confusing. But it says these two are equivalent if, first of all, the I and the J are related by the permutation coordinate of the map, and then you get this more traditional looking twisted conjugacy. Although I will just point out, these guys, the phi here is not necessarily a homomorphism. When you consider this altogether, it is a homomorphism involving the semi-direct product, but individually those things are just set maps, not necessarily homomorphisms. All right. So, the very end. I have 6 minutes on the clock. So, I said this was about Bob Brown's n-value fixed point theory and a bit more. This is the bit more part. I just want to tell you a little bit about this paper, which is pretty much finished, I believe. It's been refereed for a while, and I want to say thank you if the referee is in the audience today for making many good suggestions, and my apologies for taking so long in the revisions. But I think it's good now. We'll see. This is another AI-generated image. I just typed in this. And I wanted to see what it says. This is what they came up with. I kind of like it. I don't know what it means, but I will not refer to this picture again. But that's what the AI came up with. I will just say, I said in the n-valued theory, usually it works out the same as usual, but sometimes there's something a little interesting. This is an example where there's kind of no big surprises, in my opinion. You try to do the same constructions, and it more or less works out the way that you want it to. And I will also mention specifically, Crabbe also developed something, he didn't call it this, but something like a Reidemeister trace for n-valued maps. And I believe what I have defined is equal to his invariant, although the fundamental definitions are quite different, so it's not easy to see exactly one versus the other, but I think I should mention, Crabbe's setup is different from mine. Anyway, here's just a very basic overview. Each fixed point has a fixed point index and a Reidemeister class, like we said. And the Reidemeister trace is just a formal sum of all of these things. That's how you would write it as a formula. So you sum over the fixed points, you take the index of each fixed point, and then you multiply by the Reidemeister class of that fixed point. All right? Since the index and the Reidemeister class are homotopy invariants, that makes this formal sum is a homotopy invariant. It is a formal sum of Reidemeister classes with integer coefficients. All right? And the sum of the coefficients is the Lefschetz number. That's if you just ignore this part, then you get the Lefschetz number. And the number of non-zero terms in this sum, if you combine all the terms as much as you can, the number of non-zero terms is the Nielsen number, because that's the number of Reidemeister classes which have non-zero index. All right? So I would say that the Reidemeister trace is something like a mother invariant for Nielsen theory. Here's an example. This is a two-valued map. Each point has an index, a +1, a -1. And it also has a Reidemeister class, which I have indicated by these. Now, actually, I didn't tell you on the picture, I didn't show the whole Reidemeister class. But these two ones, they cancel out. But these other ones do not cancel with one another. This minus alpha is this one right here. It is alpha comma 1. So there's kind of two branches of this map. If you are looking at lifting it up, you get this one up here, which starts here and then comes up the bottom. So that is what I believe I called this one the 2. And then the other one, this one, which goes down here, that I called the 1. Now that's what these 2s and 1s means. It tells you sort of which branch is it a fixed point on, and then also what's the lifting element from that. So this one has that Reidemeister trace. All right. The most of the paper, if you read the paper, which I don't necessarily suggest, but if you're interested, the meat of the paper is a trace formula, right? As I said before, you don't really want to make the definition like this. You want a real trace formula, and that's what most of the paper is concerned with. Remember, the Lefschetz number looks like that. That's the trace formula, where F is a matrix with integer elements. When you want to do this for the Reidemeister trace, you have to keep track of the lifting classes, and so the entries will be things like that. Every entry of the matrix looks like a alpha comma 1 or something like that, with also integer coefficients. All right, so we end up with something like this. You can do each of those matrices for each of the lifted maps, and then you can just add them all together, and you get something like the Reidemeister trace that you want. All right. Most of the paper is showing that this is well-defined and homotopy invariant. Well-defined, I mean independent of the subdivision, which is a bit of a pain to keep track of. Yeah. So you will find pictures like this. Here's a very specific, sort of simplicial two-valued map. You will find formulas like this, which I don't suggest looking at very closely. But no real surprises. Everything more or less works the way that you would like it to. All right? So, in conclusion, I just want to say, Bob's n-value theory, in my opinion, is alive and well. He is no longer with us, but his ideas will be here with us for a long time. That's all. Thanks.